Hi all, in today's class we are going to discuss about aromaticity. Here the term aroma means smell because the initial type of compound that the scientists studied under this category were benzene, toluene, which are having very pleasant smell. So from this only these type of compound got the name aromatic compound. The importance of aromatic compound lies in the fact that these compounds are very much stable compared to the rest of the compound. So in today's class we will be discussing about aromaticity. In today's class, we'll discuss about three type of compound under this category. So according to aromaticity, we'll divide the organic compounds into three. Either it can be aromatic or it can be anti-aromatic or it can be non-aromatic. So in today's class, first we'll discuss about aromatic and anti-aromatic. Then we'll come back to non-aromatic compound. So for easiness, we'll denote aromatic as A, anti-aromatic as A dot A, and non-aromatic as Na in today's class. So first we'll see what is aromatic and what is anti-aromatic. So for a molecule to be aromatic and anti-aromatic, the first 3 points are same. It should be cyclic, it should be planar, and it should be conjugated. Here cyclic means the molecule should form a cyclic ring. If there is no ring in the molecule, then that molecule is not aromatic or anti-aromatic. So the first criteria is that it should be cyclic. That means a ring should present in the molecule. And the second criteria is that the molecule should be planar. Here it means that the end atoms in the molecule should be either sp hybridized or sp2 hybridized. Suppose in our molecule there is a sp3 hybridized carbon or any atom, then the structure of that atom is tetrahedral. That means it will lead to the non-planarity of our molecule. So for molecule to be either aromatic or anti-aromatic, all atoms should be either sp2 hybridized or sp hybridized. There should not be even one sp3 hybridized atom in our molecule. The third point is that the molecule should be conjugated. Okay, the conjugated as means that a complete delocalization of pi electron should present in a molecule for the molecule to be aromatic or anti-aromatic. This we can say in one more way that a p orbital should present on each atom of the molecule for the molecule to be aromatic or anti-aromatic. To explain this point, we'll take benzene. So you already know benzene is the best example of aromatic system. Here, 6 carbon atoms are there and all carbon atoms are sp2 hybridized. So we'll see how the structure of benzene made. For that, first we'll take carbon. Carbon electron configuration is 1s2, 2s2 and 2p2. It is in ground state. So we'll draw 2s and 2p orbital here. In 2s, 2 electron. In 2p, 2 electron. In now we'll draw the carbon in excited state. Again, we'll draw 2s and 2p orbital. In excited state, one of the electron in 2s will move to 2p. And if you are looking at the structure of benzene, every carbon atom is sp2 hybridized. So here we'll get sp2 hybridization here. We'll get 3 orbitals of sp2 hybridized orbital and one orbital, that one p orbital with one electron, is unhybridized. This is a benzene. We are taking this carbon. In this carbon, there is 3 sp2 orbitals are there. 1, 2, and 3. And that is 1, 2, and 3. That is 3 orbitals. And out of these 2 sp2 orbitals, this carbon is using for making sigma bond with other carbon atom, that is neighboring carbon atom. That is this bond and this bond. Okay. And the remaining sp2 orbital, that is this sp2 orbital, this carbon is using for making a bond with hydrogen. Because in benzene structure, we know there is a CH bond in every carbon atom. So here, the third sp2 orbital, this carbon is using for making a bond with a hydrogen atom. So these 3 orbitals are used. Now look at the unhybridized p orbital that is presenting on this carbon. So we know there are 6 carbon atoms are there. So in every carbon atom, there is a unhybridized p orbital which is having 1 electron. So in this carbon atom, we will draw this p orbital like this. It will be perpendicular to the plane. Okay. And every carbon atom, that p orbital with 1 electron is present. And there is 1 electron in this p orbital. Now, the delocalization of electron is possible by the movement of electron through this orbital. Due to overlap of this orbital only, the C double bond C, that is this bonds, formed in the benzene structure. So this is structure of benzene. You can see an hybridized p orbital on each carbon atom, which is making this delocalized. So that's why the benzene is aromatic molecule. So this is a third criteria for a molecule to be either aromatic or anti-aromatic, that it should be conjugate or a p orbital should present on the each atom which is able to take part in the delocalization. As of now, the 3 points are similar for both aromatic and anti-aromatic. Now we will discuss the fourth point. Here the fourth point is the point which is differentiating between aromatic and anti-aromatic. That point is the Huckel's rule. Suppose our molecule is obeying Huckel's rule, then it will be aromatic. Suppose our molecule will not obey Huckel's rule, then it will be anti-aromatic. Okay, so what is Huckel's rule? Huckel's rule is that suppose if our system is cyclic, planar, and conjugated, if it is containing 4n plus 2 pi electron, then that system will be aromatic. That is what is Huckel's rule. So, if a system is containing 4n plus 2 pi electron and is cyclic, planar, conjugated, that system will be aromatic. Here, that 4n plus system, n will be 0, 1, 2, 3, etc. Suppose n is equal to 0, then 4 into 0 plus 2, it will be 2 electron system. Suppose n is equal to 1, then it will 4 into 1 plus 2, it is 6 electron system. If n is equal to 2, it is 4 into 2 plus 2, it will be 10 electron system. So if our system is containing either 2, 6, 10, next will be 14, then it will be 18, etc. number of electron, and is cyclic, planar, conjugated. That system is called aromatic system. Okay, so this is aromatic. So now we'll go to the anti-aromatic. Anti-aromatic molecule which is not obeying Huckel's rule. That means it will not containing 4n plus 2 pi electron. Instead, it will contain 4n pi electron. Okay. Here the n will be 1, 2, 3, etc. Suppose our n is equal to 1, 4n is equal to 4. Suppose our n is equal to 2, then 4 into 2 will be 8. If n is equal to 3, 4 into 3 will be 12. So if our system is containing 4, 8, 12, next will be 16, 20, etc. number of electron, and is cyclic, planar, conjugated. That system we will call it as anti-aromatic. So to conclude, aromatic is a cyclic, planar, conjugated system which is containing 4n plus 2 pi electron. And anti-aromatic system is a system which is cyclic, planar, conjugated, and it is containing 4n electron. So the only difference between aromatic and anti-aromatic is anti-aromatic will contain 4n pi electron, but aromatic will contain 4n plus 2 pi electron. Other 3 points, that is cyclic, planar, conjugated, is common for both aromatic and anti-aromatic. Now we'll take 2 examples and see whether it is aromatic or anti-aromatic. The first example is, if you are looking here, the first criteria for a molecule to be aromatic is it should be cyclic. If you are looking at benzene, it is cyclic. We can see a ring here. So the first point is correct. It is a cyclic. And the second point is that it should be planar. If you are looking at the ender carbon atoms is sp2 hybridized. That means it is planar. So the second point is also valid. And the third point is that it should be conjugate. Here in this benzene structure, there is alternate double and single bond is present. If alternate double and single bond is there, then that means that system is conjugated. So the benzene molecule. Third point is that we have to find whether foreign electron is 4n plus 2 electron is present in the molecule. There are total 3 pi bonds are present in our molecule. So total number of electron is, it will be 6 electron, and 6 is an example of 4n plus 2 system. So here benzene is cyclic, planar, conjugated and containing 4n plus 2 pi electron. So that's why benzene is a aromatic molecule. Okay. Now we'll look at the second example. Here it is chlobutadiene. If you are looking here, the first point is that it should be cyclic. Our molecule is cyclic. So the first point is correct. And the second is that it should be planar. Here the entire carbon atoms is sp2 hybridized. So that's why it is planar. The second point also correct. Third point is that it should be conjugated. in the molecule, we can see alternate double and single bond. So that's why it is conjugated also. And now we have to see how many number of electron present in our system. We can see 2 pi bond, 1, 2, 2 pi bonds are present. So 2 pi bond, that means total number of electron is 2 into 2 will be 4 electron. So it is an example of 4n system. So our molecule here is cyclic planar conjugated and containing 4n electron. So it is an example of anti-aromatic. Okay, that's how we'll find out whether our molecule is aromatic or anti-aromatic. So as of now, we have discussed what is aromatic is and what is anti-aromatic is. Now we'll go to what is non-aromatic is. So for a molecule to be either aromatic and anti-aromatic, we told that the complete delocalization of pi electron should present in our molecule. So in non-aromatic, what will happen? For a molecule to be non-aromatic, there will be no delocalization of pi electrons at all. And now we'll discuss a few criteria where the molecule will become non-aromatic. Okay, the first one is that all acyclic molecule. So first point for aromatic and anti-aromatic was the molecule should be cyclic. So the first criteria to be non-aromatic is that the molecule should be acyclic. So what at all condition is making a molecule aromatic or anti-aromatic? If you are taking the opposite of that criteria, it will become non-aromatic, right? So the first criteria is that all acyclic molecule will become non-aromatic. For example, if you are instead of cyclobutadiene, that is this molecule here, this molecule, we have seen it is cyclic, conjugated, planar, and is containing 4n system, and that's why it is anti-aromatic. Instead of this cyclo, we are taking the open chain derivative of this, that butadiene, this molecule. Here, if you are looking, this molecule is not cyclic, right? It is an open chain. So this molecule is an example of non-aromatic. Now the second criteria is a non-planar molecule. All non-planar molecule will be non-aromatic, because the second criteria for a molecule to become aromatic and anti-aromatic was the molecule should be planar. But here the second criteria to become non-aromatic is that the molecule should be non-planar. Suppose if you are taking 8-aniline, the aniline is that a monocyclic conjugated polyene. That means if we are having, suppose this one, the cyclobutadiene we already drawn, it is an example of aniline, because here we can see one cycle and it is conjugated, that alternate single and double bond is present and is polyene. Polyene means a molecule which is containing 2 or more pi electrons. So, and here cyclobutadiene we can denote it as 4-aniline. Why 4-aniline? Because the number of pi electron present in the system is 4. That's why it is 4-aniline. So aniline is the monocyclic conjugated polyenes. And one more example, suppose if you are taking benzene molecule here, it is an example of 6-aniline, because 6 pi electrons are present, and here benzene is a monocyclic and benzene is conjugated and benzene is a polyene. Benzene is a 6-aniline. If you are taking 4-aniline and 6-aniline, both these are planar, and that's why the benzene went into aromatic category and 4-aniline went to anti-aromatic category. But if you are taking 8-aniline, that the structure will come like this. If you are looking here the all bonds are sp2 hybridized, and counting the number here, it is 4 pi electrons are present. So 4 into 2, so it will be total 8 pi electron will present here. So if we may think, since it is a 4n system and since all the carbon atom in the molecule are sp2 hybridized, it will be anti-aromatic. We may think like that, but actually in reality it is not anti-aromatic, because the structure of the molecule is not like this. Instead of a planar form, this molecule will adopt a structure like this. It will adopt a tub-like structure like this. It will become non-planar. Due to the non-planarity of this molecule, even though all the carbon atoms are sp2 hybridized, this molecule will become non-aromatic. So this you have to remember. And this, due to the non-planarity of the ring, the 8-aniline will become non-aromatic instead of anti-aromatic. So 8-aniline is non-aromatic. Okay. Now, so the first criteria is all acyclic molecules are non-aromatic. Second is that all non-planar molecules will become aromatic. Okay. And if in our molecule an sp3 atom is present, that system will become non-aromatic. Here, if you are looking, here we can see one sp3 atom. So that's why this molecule is non-aromatic. In this molecule also we can see one sp3 atom, that's why it is non-aromatic. Here we can see one sp3 atom, that's why it is non-aromatic. Despite all the sp2 atoms present, if one sp3 atom is presenting in our molecule, due to that one sp3 atom, our molecule will become non-aromatic. So this is the third criteria. So as of now, we have discussed anti-aromatic, non-aromatic, and aromatic system. Anti-aromatic and aromatic, first 3 points are similar. The only difference is that if foreign system, it is anti-aromatic. If foreign plus system, it is aromatic. In non-aromatic, whatever making a molecule aromatic or anti-aromatic, if you are taking the opposite, you will take the non-aromatic. That means all the acyclic molecule, all non-planar molecule, and if one sp3 atom present in our conjugated system, all these will become non-aromatic. Okay, so if 2 or 3, if all atoms present in a molecule is sp3, then also our molecule will become non-aromatic. So as of now, we have discussed what is aromatic, what is anti-aromatic, what is non-aromatic. Now we'll see the stability order. The most stable one of all these is aromatic. As you already know, aromatic is the most stable structure. And next, we may think after aromatic, the next stable will be anti-aromatic, because anti-aromatic is having first 3 points is similar with aromatic. The only, instead of foreign plus 2, it is becoming foreign. This is the only difference, right? So you may think anti-aromatic is the next stable structure, but actually no, anti-aromatic is very much unstable, to the extent that even non-aromatic is more stable than anti-aromatic. So the stability order is that first aromatic, then our non-aromatic will come, then only anti-aromatic will come. Anti-aromatic is the most unstable system, and aromatic will become most stable system. Okay, and non-aromatic will be in between of these two. And this is a stability order. This is stability order. But if you are taking the reactivity order, so whatever stability order, the reactivity order will be just the opposite. Our aromatic is the most stable, it will be unreactive, but anti-aromatic is the unstable structure or unstable system of all three. So that's why the tendency of this molecule to take part in the reaction will be higher. So the reactivity wise, anti-aromatic will have a higher reactivity, then comes non-aromatic, then comes aromatic. Here aromatic system will have least reactive, okay, because of the stable structure of aromatic system. We'll summarize what we have been discussing until now. Suppose our system is cyclic, planar, and conjugated, then we have to look for either it is foreign system or foreign plus system. If it is foreign plus 2, then the system will be aromatic. If it is foreign system, then it will be anti-aromatic. Suppose any of three of this is violated, such that if our system is not cyclic, it will become non-aromatic. And if our system is not planar, it will become non-aromatic. And if our system is not conjugated, then also it will become non-aromatic. Suppose two of this is following and only one is not following by our structure, such that our molecule is planar and conjugated, but not cyclic. In that case, what will happen? It will be non-aromatic. For example, we'll take butadiene. In this case, it is planar because all the atoms in here is sp2 hybridized, so it is planar, and it's conjugated also because alternate double and single bond is present, it is conjugated, but it is not cyclic. That's why this will become non-aromatic. In second case, if you are taking, suppose our molecule is cyclic and conjugated, but it is not planar. For example, here if we are taking cyclooctatetraene, that is this molecule, if the structure will be like this, that is 8 aniline, that is cyclooctatetraene, but actual structure is having like this, that is doublet structure. Here you can see it is cyclic. This structure is cyclic and is conjugated also because alternate double and single bond is present in the molecule. But this molecule is not planar. It is forming a doublet structure like this. So if two are satisfied, but just one is violated, then also it will become non-aromatic. So we have to remember is, if all three are satisfied, then we have to see whether it is foreign or foreign plus system. If any of this violated, then it will become non-aromatic system. Okay. So now we'll discuss about different anilines and their aromaticity. So anilines, as we already seen, anilines are monocyclic conjugated polyene. That means there will be one ring system in the molecule and it will be conjugated. That means alternate double and single bond will be present in the molecule and it will be polyene. That means more than 2 pi bond will present in the molecule. So we'll start our discussion with 4 aniline and we'll discuss till 18 aniline and we'll see the aromaticity of each compound. Okay. So the first molecule is 4-aniline. Here this molecule also called as cyclobutadiene. Now we are going to look at each points which will make the molecule either as aromatic and anti-aromatic. If one of these criteria is broken, then that molecule will become non-aromatic. Okay. So the first criteria is it should be cyclic. If you are looking at this molecule here, you can see this is a cyclic molecule. So the first criteria is satisfied. The second criteria, it should be planar. Again, this molecule, all the carbon atom is sp2 hybridized, so it is planar also. And third criteria is it should be conjugated. And if you are looking at this molecule, we can see alternate double and single bond. That means this molecule is conjugated. The first three criteria are satisfied. That means this molecule is either aromatic or anti-aromatic. For that, we have to see the number of pi electron in the system. In the molecule, we can see 2 pi bond. That means 2 into 2, total 4 pi electron. So it is an example of 4 pi system. So if you are looking, first three criteria are satisfied. It is a 4 pi system. Then this molecule is anti-aromatic. So that's why cyclobutadiene is anti-aromatic. Okay. Now you look at the second molecule, that is 6-aniline. We have to look at 6-aniline or benzene molecule. Here we have to look at the three criteria which will make the molecule as aromatic or anti-aromatic. The first one is this molecule. As we can see, it is cyclic and all the carbon atom in the molecule is sp2. So that's why it is planar. And we can see alternate double and single bond here. So this molecule is conjugated also. Now we have to see the number of pi electron. Here we can see 3 pi bond. So total pi electron is 3 into 2. So total 6 pi electron is there. That means it is an example of 4n plus 2 system. If a molecule is 4n plus 2, then that will be an example of aromatic molecule. Now the 8-aniline we will look. So we may think this molecule, again, all the carbon atoms are sp2 hybridized. So we may think this molecule is planar. And if we are looking, this is conjugated also. And if you are looking at the number of pi bonds, total 4 pi bonds are there. So total 4 into 2, total 8 pi electron will come. It is a part of foreign system. So we may think, okay, this molecule may be anti-aromatic. But answer is this is not anti-aromatic because this molecule actual structure is kind of like this. It will adopt a doublex structure like this. It will not be having a planar structure. Instead, it will have a doublex structure. So that's why it will be non-planar. So if one molecule is not planar, then that molecule will become non-aromatic. So that's why 8-aniline will become non-aromatic. Okay. Now you look at the 10-aniline. In this molecule, we may think that in this molecule also all the carbon atom is sp2 hybridized and we can see total 5 bonds, 5 pi bonds. So it will make 5 into 2 total 10 pi electron, which is a part of 4n plus 2 system. So it may be aromatic, we may think. But actually this molecule is not aromatic because there will be 2 hydrogen atom here that is present in the molecule, which will cause the molecule to become non-planar. Due to the steric hindrance of these 2 hydrogen atom, which is coming inside the ring, which will make the molecule non-planar. Due to the non-planarity of this ring, this 10-aniline will become non-aromatic. So 8-aniline is also non-aromatic. 10-aniline is also non-aromatic. Here 8-aniline is non-aromatic due to the doublex structure of 8-aniline. And 10-aniline is non-aromatic due to the non-planarity due to the 2 hydrogen which is pointing out inside the ring. Suppose the same molecule we are taking and we are removing this hydrogen, these 2 hydrogen. These 2 hydrogen is making this 10-aniline as non-aromatic molecule. So suppose we are removing this 2 hydrogen by means of a CH2 group. We are putting a CH2 group. In that case, the CH2 group will go above the ring it will form a bridge-like structure like this. So in that case, now if you are looking at this molecule, now the pi system will adopt a planar structure. Okay. Earlier, this is not planar due to the steric hindrance of these two hydrogen. But now we removed these two hydrogen by means of a CH2 group. In that case, this molecule will become planar. Now, if you are looking at this molecule, we look at the first three criteria. This molecule is cyclic. As we can see, this is cyclic molecule. And now this molecule became planar also. And we can see alternate double and single bond in this molecule. So it is conjugated also. And if you are counting the number of electron in this 1, 2, 3, 4, 5, total 5 pi bonds. That means 5 into 2, total 10 pi electron. It is a part of 4n plus 2 system. So now our molecule is cyclic planar conjugated and is containing 4n plus 2 pi system. So it is an example of aromatic. This is same even if we substitute oxygen atom instead of carbon atom also. Suppose we are removing this two hydrogen by means of an oxygen and form a compound like this. In this case also, the same thing happen like this. This molecule will also become planar and this molecule also aromatic. If two hydrogen, then 10 aniline will become aromatic. If two hydrogen are present inside the ring, then it will become non-planar. We will go to 12 aniline. Now we look into 12 aniline. This is the structure of 12 aniline and the 12 aniline is weakly anti-aromatic. How it became weakly anti-aromatic? We'll see. So this molecule is cyclic and this molecule is planar also. This molecule is conjugated. And if you are counting the number of pi electrons here, total 6 pi bonds are there. That means 12 pi electron. So it is a part of foreign system. So this molecule is cyclic planar conjugated and is containing foreign system. That's why it is anti-aromatic. Now it is weakly anti-aromatic only. Why? Because again in this molecule also there is 4 hydrogen which will come towards inside part of ring and there will be a steric hindrance associated with this hydrogen. But so due to the steric hindrance of these 4 hydrogen, this molecule is having a tendency to go to the non-planar structure, right? But compared to 10 carbon atom, this is a kind of bigger molecule. So the steric hindrance, it can adjust compared to these two hydrogen because these two hydrogen are very close. So this will become non-planar. But in 12 aniline, it is a kind of big molecule compared to 10 aniline. So this steric hindrance is manageable, but still it is having a tendency to form a non-planar structure. That's why it is weakly only it is anti-aromatic. At high temperature, if you are giving this molecule very high temperature, this molecule may convert to non-aromatic. Remember, this molecule is weakly anti-aromatic. Okay. Now we will discuss 14 aniline. In 14 aniline also same scenario will happen. It is weakly aromatic. How it is happening? Again, if you are looking at the criteria, this molecule, as we can see, it is cyclic and all the atoms in the molecule is sp2, so it is planar and this is conjugated because alternate double and single bond is present. And if you are counting total number of pi electrons here, 1, 2, 3, 4, 5, 6, total 7 pi bond is present. That means total 14 pi electron. So it is a part of 4n plus 2 system. So our molecule is cyclic, planar, conjugated and is containing 4n plus 2 electron. So that's why it is aromatic. But now again it is weakly aromatic only because due to the steric hindrance of these 4 hydrogen which is present in the molecule. These 4 hydrogen will invert steric hindrance to the molecule. So this molecule has the tendency to go to the non-planar structure. But again, compared to 10 aniline, 14 aniline is kind of big molecule. So it is this steric hindrance is kind of manageable. So that's why it is becoming weakly aromatic. But it is not strongly aromatic due to the steric hindrance of these 4 hydrogen. At high temperature again, like 12 aniline, it may convert to non-aromatic. But suppose the same molecule I am taking and like 10 aniline, I am removing this hydrogen by means of putting CH2 group here. Suppose this is the molecule. Now, if you are looking at the molecule here, it is readily aromatic because now the steric hindrance due to these 4 hydrogen removed by means of putting CH2 group here. And this molecule is cyclic, and this molecule is planar, and this molecule is conjugated, and it is containing again 4n plus 2 pi electron. That's why this molecule is for aromatic system. So now we'll discuss 16 aniline. In case of 16 aniline, again this hydrogen, it will come close, and this will impart the instability of for this molecule due to the steric hindrance, and this will cause the molecule to go into non-planar structure. That's why 16 aniline will have a non-planar structure. So if a molecule is having a non-planar structure, that will lead to the non-aromatic character. So that's why this molecule is non-aromatic. Now, the last aniline we will discuss in this class is 18 aniline. If you are looking at 18 aniline, here this molecule is cyclic, and this molecule is planar, and this molecule is conjugated also. And if you are counting the total pi bonds here, total 9 pi bonds are there. That means total 18 pi electron. It is a part of 4n plus 2 system. So here our molecule is cyclic, planar, conjugated, and is containing 4n plus 2 pi electron. So 18 pi electron, that is 18 aniline, will become aromatic. So now we have to see the aromaticity of different compounds. So we'll start with the first molecule that is given here. Here this molecule is cyclic, and the entire atoms in the molecule including oxygen is sp2 hybridized. So it is planar also, and we can see alternate single and double bond in our molecule. So it is conjugated. So first 3 criteria are satisfied. So now we have to find the number of electron which is participating in the resonance. Here we can see 3 pi bond. That means total 6 pi electrons are participating in the conjugation. So it is an example of 4n plus 2 system. So first molecule is cyclic, planar, conjugated, and it is containing 4n plus 2 pi electron. So it is an example of aromatic system. Okay. So now we will look at the second molecule. In second molecule, again it is cyclic, and entire atoms including nitrogen, since nitrogen is a part of double bond, every atom is sp2 hybridized. So it is planar also, and we can see alternate single and double bond. That means this molecule is conjugated. Since first 3 criteria are satisfied, we have to find the number of electron participating in conjugation. Here 3 pi bonds again, and total 6 pi electron. So it is a part of, it is a example of 4n plus 2 pi electron. So our molecule is cyclic, planar, conjugated, and it is containing 4n plus 2 pi electron. So it is an example of again aromatic system. Here this molecule is an important molecule. The name of this molecule is pyridine. Okay, now we got pyridine is aromatic. Before going to next molecule, we have to compare pyridine molecule with one more molecule, that is a 5-membered ring containing nitrogen. This molecule, the name of this molecule is pyrrole. So now we have to see whether the pyrrole molecule is aromatic or not. So that we have to see whether it is satisfying the criteria for to be aromatic. The first criteria is that it should be cyclic. Here we can see our molecule is cyclic. The second criteria is that it should be planar. For a molecule to be planar, it should only contain sp2 or sp hybridized carbon. But here we can see this nitrogen is sp3 hybridized, and there is a lone pair on this nitrogen. What will happen? This nitrogen, this lone pair on the nitrogen will take part in the conjugation. That this lone pair will move here, and this pi bond will move here, and from this we'll get a structure like, since lone pair on the nitrogen move to the bond between nitrogen and carbon, a double bond will form here, and a negative charge will form here. Here for the double bond, no change happens. There is a hydrogen in the nitrogen, and since the negative charge on the nitrogen moved between nitrogen, and a positive charge will form on the nitrogen. Okay, here if you are seeing here, now every atom in the molecule is now sp2 hybridized. So now it is following the criteria that it should be planar. So second criteria also satisfied if the lone pair on the nitrogen is taking part in conjugation. Okay, the third criteria is that it should be conjugated. Now we can see from this we got a structure like this. Again this molecule is conjugated by moving this electron here. In that case this electron will move here, this electron. So entire molecule is conjugated. as we can see. So it is following the third criteria also. It is conjugated. Now we have to see the number of electrons participating in the conjugation. So for that, here this double bond is taking part in conjugation. Here this double bond and this negative. Total 2 pi bond and 1 lone pair. Here 2 pi bond means 2 into 2, total 4 electron plus 1 lone pair means 2 electrons. So total it will be 4 plus 2, total 6 electron is taking part in the conjugation. 6 electron means 4n plus 2 system. So here our molecule is cyclic planar conjugated and it is containing 4n plus 2 pi electron. So pyrrole molecule is also aromatic. Now, if you have to look at what is the difference between pyridine and pyrrole is that the pyridine is more basic because in pyrrole, this lone pair is taking part in conjugation. So, the availability of this lone pair is less. But in pyridine, this lone pair is readily available. So, the basicity is more. Okay. Both are aromatic, but in case of basicity only, the difference is coming. Now, we look at this molecule here. Now, if you are looking at this molecule here, this molecule, as you can see, it is a cyclic molecule. So, it is cyclic. Now, entire carbon in the cyclic system is sp2 hybridized. That means this is planar. See, alternate double and single bond in the system. That means this molecule is conjugate. Now, since three criteria are satisfied, we have to see number of electron which is taken part in the conjugation. While counting, we have to consider only the cyclic system. Okay. That is, you have to remember the pi bond which is present at the center. We will not count this as a part of our conjugated system because it is a kind of isolated double bond. Here, in cyclic manner, the double bond at the periphery of the molecule only we will count. So we are going to look at how many pi bonds are there. 1, 2, 3, 4, 5, 6. Total 6 pi bond. That means 12 pi electron. That means it is an example of 4n system. So our molecule is cyclic planar conjugated and it is containing 4n. So it is an example of anti-aromatic. Okay, our molecule is anti-aromatic. And this is the next molecule here. Here, while looking at this molecule, you may be getting confused to determine what kind of aromaticity this molecule is having. So we can draw this molecule in some other way. If you are looking here, there are two ketones present in molecule. So in ketone, this is a polar bond. That means this double bond will break and the electron density will go to oxygen. Here also, this bond will break and the electron density will go to oxygen. So how it will be? The same molecule will draw in some other way. Here, this bond is breaking here. So negative charge will come on oxygen, positive charge will come on this carbon. So it will be like this. And in this bond also, this bond will break. Negative charge will come on oxygen, positive charge will come on the carbon. So here it will be like this. Now we have to look at this system alone to determine whether it is aromatic, anti-aromatic or non-aromatic. Okay. So here I'll take this system alone. That is, this is the system that we have to find whether it is aromatic, anti-aromatic. If you are looking here, you can see the entire atoms are sp2 hybridized. First, it is a cyclic system. So it is cyclic. Now we have to see whether it is planar or not. Here we can see all of these atoms are sp2 hybridized. So it is planar. Okay. Now we have to see whether the conjugation is present here or not. Here the conjugation present, how it will happen? This bond will move here. In that case, a positive charge will form here and now double bond will move here and the positive charge, for this positive charge, no change at all. Now in this molecule, what will happen? This bond can move here. In that case, this will become, the double bond will come here and this for this positive charge, no change at all. Here, a new positive charge will come here. So here we can see in this molecule, the conjugation is possible. These are the conjugated structures of this molecule. So this molecule is conjugated also. Now we have to find the number of electrons participating in the conjugation to determine whether it is aromatic or anti-aromatic. So here there is only one pi bond in the molecule. So one pi bond means 2 pi electron. So that means it is an example of 4n plus 2 system. Here when n is equal to 0, Number of electron in 4n plus 2 system will be 2 electron. So 2 pi electron is an example of 4n plus 2 system. Here our molecule is cyclic planar conjugated and it is containing 4n plus 2 pi electron. So our molecule is aromatic. Okay. Now we have determined the aromaticity of this molecule. We'll move on to the next molecule. This we have already seen this molecule previously. This is pyrrole molecule. I told you here this lone pair will take part in the conjugation. In that case, every molecule will become planar. And if this lone pair is taking part in the conjugation, in that case, the total electron count will be 6 electron. Here 4 electron from the double bond and 2 electron from the lone pair. So total 6 electron will come. So it is an example of 4n plus 2 system. And our molecule is cyclic, and since every atom is sp2 hybridized, it is planar, and here we can see conjugation also in molecule, so it is an example of aromatic system. Okay, now we'll go to the next molecule. So now we have determined the aromaticity of this compound. Here we can see one oxygen atom, one carbon atom, both are sp3 hybridized. If there is an sp3 hybridized carbon atom or any atom in your molecule, then that will become non-aromatic, as we already learned. But here in oxygen, there is 2 lone pair present. So one of this lone pair can take part in conjugation. This will move here. In that case, this pi bond will move here. The end of conjugation, you'll get a product like this. You'll get a double bond between oxygen and carbon. And since lone pair on oxygen took part in conjugation, a positive charge will come on oxygen and a negative charge will come here. Here, double bond is not having any change. But still, here also, the sp3 carbon is not having any change in hybridization. Here still, the sp3 hybridized carbon is present. That means our molecule is non-aromatic. Okay. Now we'll go to the next molecule. Here, again, if you are looking at this oxygen, it is sp3 hybridized, but here there is 2 lone pair on the oxygen. One of the lone pair can take part in conjugation. It will move from here to here. In that case, this electron can move here, and after the conjugation, you will get a product like this. A positive charge will come on the oxygen, and this can continue. Now this electron can move here, this bond can move here. So like this, the conjugated structure can continue. If you are looking here, now every atom in our molecule is sp2 hybridized, and number of electron which is taking part in conjugation is 2 pi bond and 1 lone pair. So 2 pi bond, there will be 4 electron, and 1 lone pair, there will be 2 electrons. So total 6 electron is participating. So this molecule will become aromatic. Okay. The name of this molecule is furan. So we have seen the furan is aromatic because it is cyclic and it is conjugated and it is planar also, since all the atoms are sp2 hybridized and there is 6 electron present in the furan. Now we look at this molecule here. So now we'll discuss about aromaticity of this molecule. Here, this molecule, we can see a boron atom, and this boron atom is sp2 hybridized. So for this molecule to become aromatic, the criteria is that it should be cyclic, and our molecule is cyclic. So the first criteria is satisfied. Next is it should be planar. For that, every atom in the molecule should be sp2 hybridized. If you are looking, boron is sp2 hybridized and all this carbon also sp2 hybridized. So our molecule is planar. Next criteria is that it should be conjugated. No, we need to know whether our molecule is conjugated or not. So this atom sp2 hybridized means one vacant p orbital is present on the boron, which is perpendicular to the plane of molecule. Here, in case of boron, one vacant orbital is present here, but there will be no electron in the boron to contribute to the molecule. So in that case, we can see these 4 carbon atoms are conjugated because alternate single and double bond is present here, and this boron atom is also conjugated because a vacant p orbital is present on the boron, which is able to take part in the delocalization. So this molecule is entirely conjugated. So it is conjugated also. Now we need to know whether it is aromatic and anti-aromatic. For that, we need to find out the number of electron in this molecule which is able to take part in the delocalization. So we need to count the number of electron in this molecule. Here in this molecule, 2 pi bonds are taking part in the delocalization. So 2 pi bond, and In boron, there is a vacant p orbital. That means there is no electron that is coming from boron to take part in the conjugation. So from boron, 0 electrons are coming. So total, only 2 pi bonds are participating. That means 2 into 2, total 4 pi electrons is participating in the delocalization. So it is an example of foreign system. So here our molecule is cyclic planar conjugated and it is a foreign system. So it is an example of anti-aromatic molecule. Okay. We'll go to the next molecule. Here, again, our molecule is cyclic and every atom in the molecule is sp2 hybridized, so it is planar. And here, this molecule can take part in conjugation by moving this pi bond here. In that case, what will happen? A new pi bond will move here and we'll get a positive charge here. Again, this pi bond can move here. Like that, the conjugated structures will continue. So, from this we can see our molecule is conjugated also. So, third criteria is also satisfied. Now, we have to see the number of electron in this molecule to see whether it is aromatic or anti-aromatic. So, we're looking at the molecule. Only one pi bond is taking part in the conjugation. So, one pi bond means 2 pi electron. So, it is an example of 4n+2 system. So, our molecule is cyclic, planar, conjugated and containing 4n+2 pi electron. It means the molecule is aromatic. Now we have to determine the aromaticity of this molecule. Here the first criteria that the cyclic criteria itself is broken. This molecule is open chain. That means this is a non-aromatic molecule. Okay. And this molecule is cyclic and every atom in the molecule is sp2 hybridized, so it is planar also. And here in this molecule again conjugation is present by moving this bond here and this bond here. So this molecule is conjugated also. So first three criteria are satisfied. So we have to see whether it is aromatic or anti-aromatic. For that we need to find the number of electron which is taking part in the delocalization. One pi bond and one negative charge is participating in the reaction. One pi bond means 2 pi electron and negative charge means again 2 pi electron. So total 4 pi electron is participating in the reaction. So it is an example of foreign system. So this molecule will become, okay. Now this is the next molecule. Here we can see an sp3 hybridized carbon in our molecule. So that means if one sp3 hybridized carbon is present in a molecule, it will become non-aromatic. Okay. Now this is our molecule. Here, this molecule is cyclic and this molecule is, every atom is sp2 hybridized, so it is planar. And here the conjugation is present in this molecule by moving this bond here, this bond here. So conjugation is also present. Now we have to see the number of electrons which is participating in the delocalization. Total 2 pi electrons are participating here. That means 4 pi electrons. So it is an example of foreign system. So our molecule is cyclic planar conjugated and it is a foreign system. So it is an example of anti-aromatic molecule. Okay. Cool. This molecule is cyclic and every atom is sp2 hybridized. That means it is planar. And here also conjugation is present in this molecule. So it is conjugated also. Now we have to see the number of electrons which is taking part in the delocalization. So total 2 pi bond and 1 negative charge. 2 pi bond means 4 pi electron plus negative charge means 2 electrons. So total 6 electron is taking part in the delocalization. That means it is an example of 4n+2 system. So our molecule is cyclic planar conjugated and it is an 4n+2 system. So it is a aromatic molecule. Okay. Now this is our molecule. This molecule has a specific name. It is called tropylium cation. Okay. It is a C7H7 plus. It is the molecular formula of this molecule. There will be 6 carbon atoms in this molecule. If you are looking here we can see this molecule is cyclic and since every atom is sp2 hybridized, it is planar and we can see the conjugation in this molecule like this. So this molecule is conjugated also. Now we have to find the number of electrons. Here 3 pi bond taking part in the delocalization. That means 6 pi electron. So it is an example of 4n plus 2 system. So our molecule here is cyclic planar conjugated and it is 4n plus 2 also. So our molecule is aromatic. Okay. Now this molecule. Here, as we have already seen in boron, what we told, there is a vacant p orbital present in the boron, and oxygen, there is a lone pair in oxygen which is able to take part in the reaction. So this lone pair in oxygen will take part in conjugation. So it will move here. In that case, this bond will move here. So here the conjugation is present in this molecule. And since every atom in the molecule is sp2 hybridized, it is planar also. And as we can see, it is a cyclic molecule also. So first three criteria are satisfied. Now we have to find number of electron which is taking part in the conjugation. So here this pi bond, that is one pi bond and one lone pair is taking part in the conjugation. In boron, there is vacant p orbital only participating. That is, boron is contributing 0 electrons to the system. Okay. So total 1 pi bond and 1 lone pair. So 2 electron from lone pair and 2 electron from pi bond. Total it will be 4 electron. So it is an example of 4n system. So our molecule is cyclic planar conjugated and it is a 4n system. So this will be anti-aromatic. Okay. Now this molecule, suppose in the question, if you are seeing a sp3 carbon, here this and this both are sp3, but in oxygen there is a lone pair which can take part in conjugation. So it will convert to sp2. Okay. So oxygen, nitrogen, you don't mind if sp3, nitrogen, oxygen present, then the lone pair in that nitrogen and oxygen can take part in conjugation. Like that, it will convert to sp2 hybridization. Okay. But in the question, in the molecule, if sp3 hybridized carbon atom is present in your molecule, then this molecule will become non-aromatic. Okay. So if you are seeing sp3 hybridized atom in your molecule, that means that will be non-aromatic molecule. Now look at this molecule here. Here one boron atom is present. That means a vacant p orbital will be here, which is able to take part in the delocalization. The oxygen is present here. That means there is lone pair present in the oxygen, which is able to take part in the delocalization again. So how it will happen? This bond will move here, this bond will move here, and this will move here. Like that, this molecule is conjugated. And since every atom is sp2 hybridized, it is planar. And we can see it is a cyclic system also. So this molecule is cyclic. Now we have to find out number of electron which is taking part in the conjugation to find out whether it is aromatic or anti-aromatic. So in this molecule, two pi bond and one lone pair from oxygen is taking part in the conjugation. 2 pi bond means 4 electron, 1 lone pair means 2 electron. So total 6 electron is participating in the delocalization. That means it is an example of 4n plus 2 system. So our molecule here is cyclic planar conjugated and it is a 4n plus 2 system. So it is a aromatic molecule. Now this molecule, again here 7 carbon atoms are there. So the name is tropylium anion. We have seen previously tropylium cation, it was aromatic, right? Now this is tropylium anion. In tropylium anion, if you are counting the total electron count, 3 pi bond and 1 lone pair. So total it will be 6 plus 2. So total it will be 8 pi electron. That means it is an example of 4n system. So it will be anti-aromatic. But actually this molecule is not planar. So in that case, this will become non-aromatic. Okay. So you remember tropylium anion is an example of non-aromatic system. Now this molecule, if we are getting a fused system like this, what we have to see is we look at whether we can find a cyclic system of pi electron here. Here we can see a cyclic system like that, right? So here this is cyclic. Now every atom in this is sp2 hybridized. So it is planar. And here alternate double and single bond present. That means it is conjugated also. Now we have to find out number of electrons in this molecule. 1, 2, 3, 4, 5. Total 5 pi bonds. That means total 10 pi electron. It is an example of 4n plus 2 system. So this molecule is aromatic. Okay. Here this molecule is having a specific name. We'll call this molecule as azulene. And if you are looking here, there is one more thing about azulene is that this is a 5-membered ring, okay? And this is a 7-membered ring. So we have already seen that propylium cation. In propylium cation, it was a 7-membered ring. And since a positive charge present here, it became aromatic. And we have seen in case of 5-membered ring, that is this, when a negative charge presented here, in that case, it also became aromatic, right? Both these systems are aromatic. We have already seen previously. So in this molecule, what will happen is that there will be a partial charge will form in this molecule, that a negative charge will form here and a positive charge will form here, because if you are looking now, this is resembling the tropylium cation and this is resembling this system here. So a partial charge will form in this molecule and this molecule will become an ionic character, and there will be charge transfer from negative to positive charge. So that's why this molecule will become colored and it will have a blue color due to this charge separation. So you just remember in azuli, there's a 7-membered ring and a 5-membered ring. In 7-membered ring, when there is a positive charge present, it will become aromatic. In 5-membered ring, when there is a negative charge present, it will become aromatic. So a partial charge will form in this molecule, and since a partial charge is formed in this molecule, there will be a charge transfer in this molecule, and due to this charge transfer, this molecule will become colored. It will become blue color. Okay. We'll move on to the next molecule. Here, again, we are seeing a isolated double bond here. While counting the electron delocalization, we will not consider this molecule. Sorry, we will not consider this bond. Okay. So we'll only look at the peripheral electron delocalization. So if you are looking here, here it is a cyclic and every atom is sp2 hybrid, so it is planar and it is conjugated because alternate single and double bond is present. Now you have to find the number of pi bonds that is present: 1, 2, 3, 4, 5, 6, 7. Total 7 pi bond is there. That means total 14 pi electron. So it is an example of 4n plus 2 system. That's why the system is aromatic. Now look at this molecule. Here, every atom, again, this is a cyclic molecule and every atom sp2 hybrid, so it will be planar. And here also we can see the conjugation like this. So it is, this molecule is also conjugated. And next we have to see the number of electron count. Here, 1 pi bond and 2 negative charges taking part in the delocalization. That means 2 electron from 1 pi bond, and from 2 negative charge there is 4 electrons. So total 6 electron is taking part in the conjugation. That means it is an example of 4n plus 2 system. So our molecule here is cyclic planar conjugated and is 4n plus 2 pi electron. That means this will become aromatic. Okay. A special case of aromaticity that is called homoaromaticity. Here, a compound is homoaromatic means, I told you for a molecule to become aromatic, there should be a complete delocalization of pi electrons, right? So in a homoaromatic molecule, there will be an sp3 hybridized carbon atom. And to become aromatic, this molecule will surpass this sp3 hybridized atom and it will acquire a delocalization by surpassing this sp3 hybridized atom. That we'll see using an example. Suppose take this molecule. So it is a 8-membered ring. We can see 1, 2, 3, 4, 5, 6, 7, 8. So we can see 8 carbons here. And one of the carbon is sp3 hybridized carbon. And there is one cation also present in this molecule. So what will happen is that according to non-aromatic criteria that we have mentioned, if one sp3 atom is present, then that molecule will become non-aromatic. But in this molecule, what will happen is that this sp3 atom will go above the ring. And we will get a structure like this, where the sp3 atom will go above the ring and the remaining atoms will be like this. So if you are not considering this carbon here, all the other atoms is in the plane, and here we have 3 pi bonds which is taking part in the conjugation. That means total 6 pi electrons are there. So it is an example of 4n plus 2 system. And our molecule here is cyclic. And since apart from this carbon, all other carbons are sp2, and this will be planar molecule, and we have alternate double and single bond plus a positive charge here. So this will be conjugated also. So it is cyclic, it is planar, and it is conjugated, and it is having 4n plus 2 pi electron. So this molecule now it will become aromatic.